This is the solar system's weirdest planet. It's sideways, ice-cold, and completely silent. Well, it's not really silent, but if you compare it to its gas giant siblings, their constant roars could make your hair stand on end. But why is our icy neighbor so quiet? Is its magnetic field just weaker than the others, or are we simply lacking the instruments to hear its true activity? This is the space race. When scientists first detected radio waves coming from Uranus in 1951, they were shocked. They had expected to find a radiation belt similar to Jupiter's or Saturn's, but instead they found it was eerily silent. The detection of these radio waves was actually an accident. Scientists were trying to detect radio waves being beamed from Earth to Mars when they accidentally picked up a radio wave with a very low frequency that seemed to be coming from the direction of Uranus. At first, they assumed that the signal must have originated from Earth's ionosphere, which is a layer of electrically charged particles in the upper atmosphere. But after checking and double-checking their equipment and making sure there weren't any terrestrial radio sources interfering with their signals, they realized that the signal had come from deep space. And to their shock, it was coming from Uranus. You see, this was long before Voyager even passed Uranus, let alone sent back close-up images and data about it. So scientists knew almost nothing about the planet's magnetic field at the time. But they did know that it had an intrinsic magnetic field. In other words, it wasn't a magnetic field generated by any kind of currents in its interior. All planets in the solar system except Mercury have intrinsic magnetic fields. But scientists don't know exactly how planetary magnetic fields are generated. For example, on Earth, our magnetic field is created by the movement of molten iron in our planet's core. But Uranus is an ice giant, so this can't be happening in its core. In the 1950s, scientists thought that perhaps the magnetic field of Uranus was generated by a dynamo effect in its liquid mantle. Dynamos are rotating electrically conductive fluids that generate magnetic fields. The best example of a dynamo in the solar system is Jupiter's. Jupiter rotates really fast, like nearly once every 10 hours fast, which generates huge amounts of electric current within its metallic hydrogen atmosphere. These electric currents then create magnetic field lines that extend far out into the solar system. This magnetic field is so strong that it reaches as far as Saturn. But in order for Uranus to have a comparable magnetic field strength to Jupiter, it would need to rotate more than 40 times faster than it does now. And we know that Uranus doesn't rotate that fast because if it did, its shape wouldn't be nearly as round as it is. That's one theory on where the magnetic field might come from. But we can also look to Saturn for some inspiration. Saturn's magnetic field is intermediate in complexity between the more simple fields of Jupiter and Neptune and the more complex fields of Earth and Jupiter. Saturn's magnetic field is thought to be created by a combination of both the dynamo effect in its liquid metallic hydrogen and by currents in its interior. Scientists think the reason why Saturn has a stronger magnetic field than Uranus is that it has a stronger dynamo effect. Now, this is all speculation based on what we know about the inner structure of Saturn and Jupiter. We don't really know what's inside Uranus. It's just that Saturn's magnetic field is stronger than Uranus's, and it's close enough to it that scientists think the two effects must be related. So, going back to that accidental radio wave discovery, scientists had a few ideas of what might be causing Uranus's magnetic field. But ultimately, since they didn't know much about the planet, they couldn't come up with a good explanation for why it would have such a weak magnetic field. This lack of explanation is part of why Uranus is such an enigma. To understand the problem here, let's talk about Jupiter. Like we mentioned earlier, Jupiter's magnetic field is extremely powerful. It's so massive that it's visible from Earth with the naked eye. Because of this massive magnetic field, tons of charged particles become trapped around the planet, creating Jupiter's famous radiation belts. These radiation belts emit radio waves, which can be detected here on Earth. Scientists use these radio waves to map out the magnetic field lines of Jupiter. It's kind of like we're listening to Jupiter's heartbeat. By mapping out these radio waves, we can learn more about the planet's magnetic field. And if Uranus had something similar, we would be able to map out its magnetic field in a similar way. But as we discussed earlier, when scientists tried to listen to Uranus, they found it was silent. There were no detectable radio waves being emitted from its radiation belts. Okay, so at this point, you might be thinking, well, maybe its magnetic field isn't as strong as we thought. Maybe it's weaker than Jupiter's, but definitely stronger than Earth's. And maybe its magnetic field lines are too weak to trap charged particles in large numbers, meaning there aren't enough particles to create significant radiation belts, and therefore no radio waves to detect. But unfortunately, the data says otherwise. It turns out that Uranus does have substantial radiation belts. We just can't see them emitting radio waves. In 1986, Voyager flew past Uranus and detected a faint glow at a wavelength of 2.3 millimeters. What's interesting about this wavelength is that it's only emitted by particles moving at relativistic speeds, meaning particles that are moving incredibly fast. The radiation belts of Uranus are filled with electrons that fit this description. So we know that it has radiation belts, but why aren't they emitting any radio waves? This brings us to another piece of the puzzle. One of the things that makes Uranus so unique is its tilt. It rotates on its side relative to the Sun. Almost all the planets in the solar system rotate on their axes with only a slight tilt. But Uranus is tilted over 90 degrees. This means that during half of each orbit around the Sun, it essentially sees the Sun from the side, and during the other half, it sees the Sun from nearly directly above or below. This sideways view of the Sun gives us some clues as to why its radiation belts are so quiet. See, the Sun bombards Uranus with high-energy particles that get trapped in its radiation belts. These particles excite the atoms and molecules in Uranus's atmosphere, causing them to release energy in the form of light. Most of this light is invisible to the human eye, but some of it falls within the range of visible light. When Voyager passed by Uranus, it detected a mysterious glow in its atmosphere. Scientists believe that this glow was caused by the interaction of these high-energy particles with the atmospheric gases. When Jupiter sees the Sun, it's mostly head-on. So the magnetic field lines of the Sun's particles tend to run parallel to the planet's magnetic field lines. Uranus, however, sometimes sees the Sun from the side, which causes the Sun's magnetic field lines to become intertwined with Uranus's magnetic field lines. This has a couple of important effects. First, the charged particles become more tightly bound to the magnetic field lines, making it harder for them to escape. Second, they begin spiraling along the magnetic field lines, increasing their speed and thus their energy. Once they reach a critical speed, they emit X-rays rather than visible light. And third, they interact with each other more frequently. All three of these effects tend to remove particles from the radiation belts faster than they can be replaced by new particles from the Sun, resulting in quieter radiation belts. Now, you might be wondering why Saturn doesn't have the same problem. After all, it's tilted over 26 degrees relative to the Sun. While this is certainly true, Saturn is almost perfectly round, whereas Uranus is slightly flattened at the poles. This flattening means that the magnetic field lines of the Sun tend to be more closely aligned with Uranus's magnetic field lines, meaning that fewer particles become trapped, accelerated, and removed from the radiation belts. All of this data paints a pretty clear picture of what's going on. Uranus's magnetic field is actually stronger than we thought. It's just that its radiation belts are so quiet that we needed a spacecraft like Voyager 2 to detect them. Unfortunately, by the time Voyager reached Uranus, it had been many years since the initial radio wave discovery. So, to try to detect radio waves from Uranus, scientists had to search through old archived data to see if they could find anything, and luckily, they did. By reanalyzing data collected by the Pioneer 10 and 11 spacecraft, scientists were able to find radio waves coming from Uranus. What's even more interesting is that these radio waves seem to be coming from higher latitudes than expected. This could mean that the magnetic field of Uranus is actually more complex than we thought. Perhaps it has multiple layers or regions that behave differently. Maybe there are different mechanisms generating the magnetic field in different regions. Or maybe it's a combination of both the dynamo effect and currents in its interior. Just like Saturn, further study will be required to understand the exact nature of Uranus's magnetic field. There's just so much we do and know about our solar system, and it can be really exciting to think about all the discoveries we have yet to make. Who knows what we might find next? If you love space and science as much as we do, make sure to subscribe for all the latest news and updates. As always, this has been the Space Race. Don't forget to keep looking up.